now. So we're going to begin by looking at this particular equation, and this is just an idea. This is not the worst thing in the world to deal with, but I know that I can make one small change, and I literally would not even think about touching a calculator for this problem. And this is the small change that I would make. First of all, I want to talk about the fact that this side has exactly one term. I know there's a lot of things going into it. It's literally, when I look at that, I see two things being multiplied. One of the things is 0.4. The other thing is a binomial, but because it's got parentheses around it, it's just a thing. So I have something times another thing, so that's just one term. On the other side, I have two terms, right? That's a term, and with the negative symbol, that's another term. In order to tweak this equation, I'm going to propose that we multiply both sides by 10. That means that every single term, all the things that I've underlined in orange are going to be multiplied by 10. And when I do that, this equation is going to become 4 times the quantity of x minus 2, and that will equal 34 minus 2x. Now, it's a very small change, but the good news is that the amount of lifting I have to do to make that change is small. Already, I feel confident that I definitely do not need a calculator, and I can proceed without even thinking about getting one. What am I doing right now to the right-hand side? What do I call this? I did. I used the simplest form of the distributive property, and I rewrote the left-hand side. So one of the things we talked about yesterday was sometimes you just rewrite a part of the equation. It's very important that I understand when I rewrite a part of it, the thing that I write down has to be equivalent to the thing that I had. So this thing must be always equivalent to this regardless of the value of x. And I know that it is because of an area model and the simple form of the distributive property. What I'll do next is, I guess I'm just going to add 2x to each side. If I add 2x to the left-hand side, this is going to become 6 times x minus 8. And the other side is going to become 34, but you can see it, right? When I add 2x to this, there's nothing there, right? It's gone. So there's just a big nothing. If we add 8 to both sides, this is going to become 6 times x equals, what are we looking at? What is it? 42, actually. So this is going to become positive 42. And if I divide both sides by 6, I get that x is 7. So I feel happy that even though I'm not the best arithmetic person in the world, making this one little tweak at the very beginning made my numbers so much more pleasant to deal with. I like it. Now, the next one is not quite as nice. In fact, the next one is so taxing that I'm going to ask you to not write this in your notes. The next one, not write in your notes. So I just want you to watch it. And I'm going to ask, oh, but before we get to that one, I do want you to write this sentence in your notes. And just the one sentence, not the whole thing. I just want you to write this top thing. Two equations are considered equivalent to each other if all their solutions are the same. So if one equation has a value of x, or it has 2 values of x or 3 values of x, it's equivalent to another equation as long as they're producing all the same outputs. We can get equivalent equations by tweaking equations, and common ways that we do that, and this doesn't need to be in your notes, so I'm not asking you to write this part down. The common ways to do that are by adding or subtracting the same thing from both sides, or by multiplying or dividing both sides of an equation by the exact same value. So there's things that I do in GeoGebra with CAST that I really like showing, oh, these equations are the same. And we'll look at that. And it's just fun to know that you can take a really simple equation and make it progressively more complex by just doing things to both sides. But you can also take an equation and make it so simple to the point that it just says what x is by just applying these principles. All right, this next one. So this I did want in your notes. This next item is just for viewing only. So first of all, can someone tell me how many terms do I have on the left-hand side? Yes, sir. On the left-hand side? Oh, very good. It's hard maybe from your location, but there's 1, 2, 3 things, right? How many are on the right-hand side? Yes. Again with the what? Okay. So on this one, multiplying by 10 would help me out a lot. But if I wanted to get rid of all the decimals, what should I multiply both sides by? Yes, sir, Max. 10. He's got the hands up. I see that. Yeah. 10. If I multiplied both sides of this by 10, not by 10, by 100, right? That will take all of them, including this one. This was the only one that was problematic. Now, admittedly, these numbers are a bit large, but they're not unreasonably large. So I'm going to go ahead and rewrite this using this property. This becomes 750x squared. What's the next term?
48x.
And then the next term?
Wait, no, 30.
And then the last one is minus 30, correct? So again, to multiply by 100, I'm just moving the decimal place 2 to the right. How about the other side? What's the first term? Yep. The next one is 1002, and then I've got minus 1000 x squared. I will point out on the right-hand side, these two are like terms, and conveniently, when I combine them, I get exactly negative 750 x to the second power. And the reason why that matters to me is I'm just going to point this out in this line that, yeah, precisely, this, right, will combine with this. And I do want to point this out, and maybe you can see this not in the classroom, but maybe not. But just because you see the exact same coefficients, be careful. So do you see this? There's a negative 3x here and there's a 3x here. Okay, I've seen you do this in the class. You see those, and it's so compelling for you because if they were right next to each other on the same side of the equation, they equal 0. But I've seen some of you literally draw lines like this and put the number 0 above it like that, right? And it's a problem because literally what's happening, if you think that these two just go away, what you're literally doing is on this side, you are subtracting 3x, and on this side, you're adding 3x, right? And you can't do that to both sides. If you're going to do something, you have to either add the same thing or subtract the same thing. But you can't add and then over here subtract the same thing. So be consistent. These, right, are both exactly negative 750, so there's not a problem with me ignoring that. And my equation collapses to 480x minus 30 equals, it's just going to be, yeah. If I undo this subtraction of 30 by adding 30 to both sides, we get 1032. And then therefore x is 1032 divided by 480. At no point in this problem did I feel compelled to grab a calculator and check arithmetic, right? Because we're basically just sitting here. Where did I put my calculator though? Because we're just sitting here and we're just typing in values, right? And as we type, oops, get back up to there. And as we type in those values, you can see, and now at this point, I do want to grab a calculator. So I'm going to take the 1032 and divide it by 480, and we get exactly 2.15. So x is 2.15. And that's a fine answer because notice this decimal terminates there. It doesn't, there's not more digits. If there were a lot more digits, if it filled your screen, I would want a reduced fraction. So because you're not throwing information away. So I would also say that this is 43/20ths. This is an easy process on your calculator. If you don't know how to do that with your particular calculator, bring it up and I'll show you. It's pretty simple to ask it to reduce fractions like that. All right, so this one was not in our notes, but we're going to move on. And we are now going to look at this. If you could please jot this down into your notes. And it turns out that not only can you multiply both sides by a value to reduce complexity, you can also divide. So again, I don't see any more than 3 terms, right? The left-hand side has 1 and then 2 terms, and the right-hand side just has 1 term. But we're going to either you can think to divide both sides by 1,000, or you can say we're multiplying both sides by 1/1000th. And when we do that, all of a sudden we end up with 2 times the quantity of x minus 24 plus 5 equals 18. That's definitely worth the transition, right? Because some of those large numbers with those coefficients, it would be difficult for me to do that without a calculator, perhaps. The next thing I'm going to do is I'm going to undo the fact that 5 is being added to that by subtracting 5 from both sides. So I'm going to have 2 times the quantity of x minus 24 is equal to 13. I'll rewrite this using the distributive property. 2x minus 48 is 13. And if I add 48 to both sides, what is that? 58, 11. So 61. 61. So x is 61 halves. Sometimes I see you guys struggle with this last step. And in fact, sometimes when you're doing problems, you'll get to this part where your 2x is 61. And because 2 doesn't go in there evenly, and your mind can't just say, if that was 60, you would write x is 30. But that being 61, I've seen some of you stop there, okay? You don't have to stop there, right? You don't have to stop there. Just show me that you're dividing both sides by 2. So if you just write this, right, you're done. And I'm very happy with that answer, especially if I don't ask you to reduce the fraction. It's good to think about that and do it. But also, like when you have this, right, I know that you would just write down x is 30, but do this for yourself. Just say, oh, that is this. So that you can get really comfortable with the fact that all you're doing is dividing both sides by this coefficient. You're undoing this multiplication to figure out exactly what x is. All right. We are moving on now to the topic that I most like, the topic that I titled this lesson on, and it is the fraction busters. So if you could please write this equation down. Again, there's only 3 terms, 2 terms on the left-hand side, I like to point that out, and a single term on the right-hand side. And without a lot of motivation right now, I'm going to begin this problem by pushing a factor of 6 across all 3 of those terms. Every single one of those terms is going to get a new factor of 6, not 1/6. I'm not multiplying by 6 over 6. I'm going to push a factor of 6 across all 3 terms. So I want you to write exactly what I write below. This is going to become 6x over 6 minus 6 times 5 over 8 equals 6 times 4. By taking the moment to write this step, you can see every single one of these 3 terms just got a shiny new factor of 6. You got a 6, you got a 6, everybody got a 6. You see it? So we pushed a 6 across all of them. You see it? Now, the reason why that's convenient is because it quickly, right, identifies the fact that there's a giant 1 here now, and I've just eliminated one of my 2 fractions. So this problem becomes x minus 30 over 8 equals 24. I would say that we're not entirely done there, though, because I still have a fraction. And I think it's worth it for me to think about this fraction and rewrite a part of this equation by just identifying the fact that this value has a giant 1 hidden in it. So this fraction, 30 over 8, is equivalent to x minus 15 fourths, and that equals 24. So in this step, when I go from here to here, right, what did I do? What would we call that from yesterday? I did reduce the fraction, yeah. Well, we called it rewriting, right? So when we are engaged in rewriting, right, the important thing is that I need to be able to visually go back and forth and ensure that the thing that I wrote down, right, the new thing that I wrote down, this has to be exactly equivalent to the thing that I had before, right? So you can rewrite, but you have to make sure that when you're rewriting parts of it, what you get is always the same. All right, we're going to finish this problem by pushing across what factor? Yes, exactly. Thank you. We are going to push across a factor of 4. So this is going to become 4x minus, you know what? I'm just going to show this. Look at this. You can see if I push across a factor of 4 to that term, isn't this just going to become minus 15?
Yeah.
And that's going to equal 4 times 24, which is, I believe, 96. Something like that. Now, if I add 15 to both sides, it's not the nicest number in the world, but it is a nice number. It has some, actually, it's kind of cool. 111. Is that right? Yeah. Okay, so hey, watch this. I'm still not grabbing a calculator. Right, there we are. It's 111 fourths. And I honestly, I mean, if that could be reduced, it's nice to do it. And you may be saying like, but can I reduce it? I don't know. But if it's something that's reducible pops up in your mind, I'll almost always accept that non-reduced answer as you just go through and show your work. But what I don't like is if you guys, this does not have a repeating decimal. So you could also write this. This would be acceptable, 27.75. But if you had a number where the decimals just went off the screen, you've got to give me this. Because the thing is when you truncate or when you round an answer down, you're throwing information away. This contains, well, for example, 2/3, that contains a lot more information than 0.6. In fact, 0.6 is a terrible approximation for this, right? So these are not the same. However, we have a symbolic way to fix it, right? How can I make these the same? Exactly. So at that point, they are the same. Okay. So I have one final example that I'm going to do with you, and then you guys are going to do 2 on your own. And again, we're thinking about this idea of eliminating fractions, fraction busters. So this is the next problem we're going to do. And on this one, please write it down like this. Again, I like to point out what I see here. I see 1, 2 terms on the left-hand side and a single term on the right-hand side. The reason why I point that out to myself is because I know if I choose to push across factors to all of those terms, I have to make sure each one of them gets these new factors. I am going to push across the factors 3 times 2, 3, 2. And the reason why I'm doing that and not the 6 is because I know if I push 3, 2 across and put that in all the numerators, it's going to make it easier for me to identify ones that I can get rid of. So in the first instance, I'm going to have the 3, 2, and then I've got the 5x. So you can see what I did, and then over 3. The next one's going to be the 3, 2, and the 15, and that's over 2, equals the 3, 2, the 5, all over 2. So our ones, right? We have a 1 in the form of 3 over 3 that we can eliminate. We have a 1 in the form of 2 over 2 and another 1 in the form of 2 over 2. So having gotten rid of all of those ones, you can see there are no fractions left. This equation collapses to 10x plus 45 equals 15. If I take away 45 from both sides, that's negative 30. So 10x is negative 30. And dividing by 10, we get that x is negative 3. So just be aware of the fact that you can do these in one step, but instead of taking all the factors and multiplying them together, it's probably better off if you leave them separated out like that so that you can quickly see the ones that you've produced and get rid of the ones. Otherwise, you're going to have to, like, reduce fractions. But if they're already in their factored form, it's a lot easier to reduce those fractions. Okay, last 2 problems that I'm going to have you do are here. But there's a little bit of a problem for this. Do you guys see how they both have x's in the denominators? Right? So if x was what number what value of x would create a problem for this? There's one thing x could be that would make this terrible. Yeah, and you're saying it, it would be 0. So when I look at this and I see, okay, these denominators, right, have a value of x can't be 0. So it's always a good idea to look at your original equation and right off the bat just say, hey, if I do this entire thing and I get that x is 0, I need to point out to myself that there is no solution because that's exactly what x can't be. So that's kind of a restriction on the domain of these functions, or not functions, these equations. The solution cannot be 0 because of that. Then this would become undefined, or this would be undefined. But if you're looking at it, what would I push across here to get everything to go away? Yes, sir. No. What would I push across if I wanted all the fractions to go away? Yes. And? Yeah. We would throw 8x to each one of these, right? So this is going to get an 8x, this is going to get an 8x, this is going to get an 8x. Over here, I'm just going to suggest if you multiplied this, and this all by 100, you're not going to have this decimal, and then you could push out something to get rid of the fractions as well, okay? So just go ahead and take a moment, give you about 5 minutes to do both of those problems, and then we'll check your work. For all of you that are at home right now and doing those two problems, I was going to stop this video, but I'm going to keep it running until I can at least write down the answers and you can check your work.
With this, since you're multiplying by like 8x, or would it be 8 times x? So then it would just be 40.
Well, the thing is 8 times, yes, 8 times x is the same thing as 8x. So when you put an 8x there, the x's are gone, and that's 40, precisely.
So then, like with this, it would just be 16.
Yeah, well, negative 16x.
Okay.
Yeah.
Because this has x.
Because this has x below, you can see that x over x would make a 1.
Oh, okay.
Uh-huh.
You didn't say good morning to me, Mr. Roberts.
Good morning.
Hi, Lucy.
Hi, Lucy. Good morning.
Good morning.
Yeah, it is still 11:06. We have Lucy. What else is in here? It says there's 13 of you in here. We've got, oh, and some of you have cameras on. That's very nice. There's Lucy.
It's right here.
Amira, Aubrey, Devin, Gwen, Ian, Lauren, Lily, Maya, and Nicole. Okay, so what did we get at the answer for the first one? Yes, sir. I don't believe so. No.
40 over 27?
No. Yes. Really? What'd you get? You got 8? You got it wrong? 8 times 5 is 40? Oh, yeah, yeah, yeah. Well, I don't think it's 27.
I don't know, that's just.
So that's interesting. And that did not happen last period. So let's take a look at this. What are we pushing across all of my terms? Thank you. And I don't, yeah, exactly. So this first term, right, is, I'll just write them. It's going to be an 8x, and then there's a 5 over x minus 2 times 8x equals negative 11 times 8x over 8. So I can clearly see that these are gone, that this is gone, right? So what we're left with is 40 minus 16x equals 40 minus 16x equals negative 11x. Ooh. So I need to add 16x to both sides.
That's right.
Whoa, 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 look at it. So I'm going to add 16x to both sides.
I see what I did there.
So over on this side, doesn't this become 5x?
Yeah.
5x is 40, therefore, yeah, x is 8.
That makes more sense.
Okay, what about the other one?
I didn't get to that.
What'd you get? You didn't get to it. Okay, let me leave this up for a little bit more. Yeah,
I got it.
yeah,
I got mine.
it's undefined. So you saw that you got x was 0? No,
No, he said if you get x to 0, you have to reveal it. You said
I didn't.
no, he said if it's undefined, you're doing it wrong.
I did? I said a lot. Yes. What'd you get? Yeah, you're the third person that said that. Very good. So those of you that are at home, I'm just going to turn this off. The answer is 2. And I would probably do this. It might be a little bit overkill, but I would probably do this as a first step.
Yeah, how is this 7?
Oh, there's not 7x, it's 2x. Yeah. So basically what I did was I multiplied 325, right? I multiplied both sides by 100. And now to get rid of the fractions, I would push across to 2x. So it's one approach. Okay, I'm going to turn off the video. Thank you for everyone who joined us remotely. I will post this online almost instantaneously, and I'll see you all later.